Generative AI feels like magic, doesn't it? It can conjure up these unbelievably realistic photos, worlds that exist only in our imaginations. But right under the surface of all that magic, there's something weird, something that doesn't quite add up, a kind of ghost in the machine that's responsible for these truly bizarre, nonsensical mistakes. And in this explainer, we're going to go ghost hunting. So let's get right to it. This is the big question, the one you've probably asked yourself 100 times scrolling through generated images. You see something that's 99% breathtakingly perfect, but that last 1% is just so deeply, fundamentally wrong that it makes you question everything. So what is actually going on under the hood? I mean, we've all seen this, right? The lighting is flawless, the skin texture looks real enough to touch, and then you count the fingers, and boom, the whole illusion just shatters. You're immediately thrown deep into the uncanny valley. It's this incredible mix of being both super impressive and just deeply unsettling. Or how about this one? You have a model that can perfectly calculate the subtle physics of light reflecting off a metal sign, but it can't spell the word stop. Instead, you get this kind of dream speak, these letters that look familiar but mean absolutely nothing. It's another one of those classic glitches that just doesn't seem to make any logical sense. Here's the thing, though. These aren't just random bugs. They're clues. They're like little breadcrumbs that lead us back to the very nature of how these systems work. And maybe more importantly, they are the forensic evidence for how they break. So if we follow these clues, we can build a way, way better intuition for how these models actually think. All right, so to really crack this case, we have to start from the ground up. We're going to build the core ideas from first principles, peel back the layers, and really see what's happening inside the machine, starting with the absolute foundation of how these images get made in the first place. At the heart of almost all modern image generators is this process called diffusion. And the best way to think about it is to imagine a sculptor, but instead of a block of marble, she's given a block of pure, chaotic, shimmering television static. Her job, which the model has learned to do, is to look into that chaos, see the faint ghost of an image, and then, step by step, carefully chip away all the noise to reveal the picture that was hiding inside all along. So if diffusion is the process, the tool that does the sculpting is an architecture called a unit. Now, it looks complicated, but the idea is actually pretty intuitive. On the left side, the encoder is like an artist squinting at a scene. It zooms out, blurring the details to get the gist, the overall composition. Then, on the right side, the decoder starts to zoom back in, filling in the fine details. But here's the absolute magic trick. Those arches going across, the skip connections. They're like little post-it notes the network leaves for itself saying, hey, remember that little texture from the original? Put it back right here. Without those, you just get a blurry, indistinct mess. But okay, how does our sculptor know what to carve out of the static? That's where your text prompt comes in, thanks to something like Clip. You can think of this embedding space as a massive 3D star chart of, well, pretty much every concept imaginable. Clip's job was to learn where everything goes on this map. It figured out that the words, a photo of a cat, belong in the exact same region of space as thousands of actual pictures of cats. So when you type your prompt, you're not really writing words. You're giving the model a destination, a set of coordinates on this giant conceptual map. So we've given our model a destination, but how strictly does it have to follow our directions? Well, that's where classifier-free guidance comes in. You can literally think of it as a creativity dial. If you turn the guidance scale way down, you're telling the model, hey, here's the neighborhood on the map, but feel free to explore. Surprise me. But if you crank that dial way up, you're saying, go to these exact coordinates. No detours. I want exactly what I asked for. It lets you trade off between creativity and sticking to the prompt. Now, this whole elegant dance of noise, maps, and guidance leads us into a really easy but really dangerous trap. We see the incredible results, and we assume it understands. We think there's a mind in there. But the truth, as Jamie Taylor puts it so perfectly here, is that's not what's happening. These aren't minds. They are massive statistical pattern matching engines. They are masters of imitation. And getting that distinction, emulation versus genuine understanding, is the absolute key that unlocks this entire mystery. And that brings us right to the heart of the problem. If these are just brilliant mimics trained on a vast library of human culture, what happens when they start training on their own imperfect creations? What happens when the echo becomes the source? I just love this analogy from Reddit user Uamish Agnos. It's so good. Think about making a photocopy of a photocopy of a photocopy, right? With each copy, you lose a tiny bit of sharpness, a bit of detail. The blacks get a little muddier, the whites get a little blown out. If you do it enough times, you're eventually left with just a gray, blurry smear. You've completely lost the original signal. That, in a nutshell, is the intuitive idea behind model collapse. And this isn't just a metaphor. Thanks to some fantastic research from Ali Borgi, we can actually watch this happen. Think of all the real-world data, every picture of a cat on the internet, as a vast mountain range. You have huge peaks for common things like tabby cats, but you also have tiny, weird valleys and foothills for all the rare and strange-looking cats. Now, as the model starts recursively training on its own output, watch what happens. That landscape starts to erode. The sharp peaks get smoothed down, the weird valleys get filled in. The model is averaging everything out. Eventually, all you're left with is one single, boring, perfectly average hill. All the diversity, all the interesting outliers, they're gone, forgotten. And I know this looks intimidating, but you really don't need to parse the math to get the crucial insight here. That W stands for Wasserstand distance. It's basically a measure of how much work, how much dirt you'd have to shovel to make the model's generated mountain range look like the original, real one. And what this equation proves, with mathematical certainty, is that with each recursive training loop, that's the little n in there, that distance is guaranteed to get bigger. The model is mathematically doomed to drift further and further away from reality. It inevitably forgets. Okay, so failures in the wild, connecting theory to reality. We now have our theory. These models are statistical mimics that get trapped in an echo chamber, smoothing out the weird details of the real world. Now let's use that idea to go back to those bizarre mistakes from the beginning, because suddenly they start to make a whole lot more sense. Let's start with hands, the classic AI nightmare. It really is a perfect storm. They're complex, they can move in a million ways, and they look different on everyone. But here's the real kicker. Think about the training photos. How often do you see a perfect, clear, well-lit picture of a hand? Almost never. They're blurry, they're holding things, they're half cut off by the frame. The training data is a mess. So when the model tries to find the average hand from all that messy data, it collapses to this weird 6 or 7-fingered mean. It just knows a hand has around 5-ish long things on it. And of course, our brains are so finely tuned to spot that stuff, it just screams wrong at us. And what about that gibberish text? This one is fascinating, and it's all about how the model sees language. Here's the key. The model doesn't see individual letters. It doesn't even see whole words. It uses a shortcut called byte pair encoding that chops words into common chunks. So a word like unbelievable becomes un, believe, and able, which kind of makes sense. But it means the model has absolutely no concept that the word spelling is made of an S, then a P, then an E, and so on. It's like trying to write a sentence using a keyboard that only has a few thousand common syllables instead of letters. You could capture the vibe of a word, but you'd have no way to actually spell it correctly. And the complexity just keeps going deeper. Some of the newest models, like Flux, basically use 2 different brains to read your prompt. You've got the T5 encoder, let's call it the storyteller, which reads your full descriptive sentences to get the whole narrative context. But at the same time, you have the clip encoder, the stylist, which just scans for key words to define the visual attributes, like metallic, dynamic, or rippling. Now, this is super powerful, but it just shows how many layers of statistical interpretation and potential for misunderstanding are sitting between your idea and the final picture. So we've gone on quite a journey here, from the sculpture in the static to the photocopy of a photocopy. Let's try to distill all of it down into 3 powerful mental models, 3 big ideas you can take with you to make sense of any of these systems. Okay, number 1, the averaging catastrophe. When a model feeds on itself, it forgets the weird, interesting outliers, the tails of the distribution. It collapses reality down to a safe, bland, statistical mean. Number 2, representation is everything. The model can only be as good as the way it sees the world. If its eyes are flawed, like seeing words as jumbled syllables, its output is going to be flawed. It's a garbage in, garbage out problem at the most fundamental level. And finally, number 3, and this is maybe the most important. The model is a map, not the territory. It has a perfect, impossibly detailed map of human creativity, but it has never actually been to the place it's describing. It can mimic the form of an idea perfectly, but it has 0 true understanding. It's emulation, not cognition. And all of this leaves us with one last, pretty big question to chew on. We've seen that model collapse is basically a mathematical certainty when these systems learn from their own output. So, what happens when the internet itself, the training data for all future models, becomes more synthetic than real. What happens when our digital world becomes a photocopy of a photocopy? Are we running the risk of a kind of collective, cultural model collapse, forgetting the rich, messy, diverse reality of human creation in favor of a smoothed out, perfect statistical average? That is a question worth pondering.